warm up. The first equation is already solved for y. Yesterday's lesson, we had to do that work ourselves, right? Solve one of them for one of the variables. Today, that first one's already solved. So if y equals 5x minus 7, I take that, I plug it into the other equation for y. Now, this problem has an obnoxious amount of negatives, but we can handle it. So the first thing I'm going to bring down this negative 3x, and one common mistake when there's a negative at the very front of the problem is students drop it off. They just forget to bring it down, but you don't do that. So I'm going to bring down the negative 3x. I'm going to distribute this 2, but what kind of 2 is that? Negative. So that negative comes along for the ride, there and there. So negative 2 times 5x is negative 10x. Negative 2 times negative 7, plus 14. And so now on the left-hand side, the x's combine. Negative 3 and negative 10 is negative 13. So now I have this one equation with only one variable, which is exactly what I needed. Because remember, when it still has two variables, we can't solve. What do I do next here? Yes, subtract 14. So I get negative 13x equals negative 26. Perfect. Positive 2. And yeah. So x is 2, which is great, but I also need what? A y. So I'm going to take, yeah, which one? Top? Let's do the top. Could I have done the bottom? Yep, absolutely. So I put x equals 2 into the top equation. That gives me y equals 5 times 2 minus 7, which is 10 minus 7, which is 3. And how do I write my final answer? Yes, parentheses, x, comma, y, parentheses. And so this happens to be 2, comma, 3, parentheses. Okay, perfect. What we're doing today is still solving a system of equations. So it's got two equations with two variables. Wait, hold on, that's just page 2 I'm giving you. Sorry. Our answers will still look like a point, an XY ordered pair, but the method we're learning today is something called elimination. So Monday we did graphing, yesterday we did substitution, today we're doing elimination. So this is the first page that I'm giving you right now. We're going to start with two real basic examples, and then we're going to level up a little bit, and then we're going to do a word problem, and that'll be that, okay? So here are the steps for elimination. The first thing you want to do is make sure your equations are in standard form. So that means the x's and y's are on the left-hand side of the equal bar, the equal sign, and the constant is on the right-hand side. Now, this method is really good for this form. If you look back at the warm-up, this first equation is not in that form. So for a situation like this, you would think, oh, this is a really good for substitution. It's not really good for elimination, and you'll see why here in a bit. So in our example, step 1 is already taken care of for us. Step 2 says, find the variable that has opposite coefficients. Does anybody remember coefficient, that's a real mathy word. What is the coefficient? What do you think? That 3 in front of the x, that is a coefficient, okay? It's the numbers in front of the variables. What's the coefficient in front of this x right here? What about this y? What about this y? Right? So those are the coefficients. So step 2 says, find the variable that has opposite coefficients. So what does that mean to be opposite? Like, what if I said, what's the opposite of 2? What would you say? Negative 2. So looking at this system, which variable, x or y, already has opposite coefficients? X or y? When you look at the two different equations, the y does, right? Because in the first equation, it's a positive 1y, and the second equation is a negative 1y. Well, okay, so let's talk about 1 and negative 1. When I add 1 and negative 1, what do I get? When you do 1 plus a negative 1. 1 plus 1 is 2, but you get 0, okay? So here's the thing that we're going to be talking about a lot today. when you have the same number with opposite signs and you add them, they cancel each other out. So what we're going to do, so step 2 is find the variable that has the opposite coefficients. So let me erase that so you can see it more, the original more clearly. So we said that was the y's because that's a positive y, that's a negative y. And then it says add the two equations to eliminate that variable. So here's what I mean. We're going to add these two things just straight up and down. And the reason we can do that is because this left side equals that right side, this left side equals that right side. If I add them, it's still true that everything on that left is equal to everything on the right. So adding up and down, what's x plus 3x? Add those. What do you get? 4x. And when I do positive y plus a negative y, what happens then? Yeah, they cancel or eliminate. That's why it's called elimination method. Okay, I eliminated that variable altogether. And then when I add on the right-hand side, I'm going to get 13. I don't want you to have 13 because it's going to give you a decimal. Change this 7 right here to a 6. Yeah. And so when I add on the right-hand side, 6 plus 6 is 12. So now I have this equation. How many variables are in that equation that I have now? 4x equals 12. Just one. And I can solve for that. Now that's easy because there's just one variable. What do you do to both sides? Divide by 4. So x equals 3. And now after this, the process is the exact same as what we did yesterday. You take x equals 3 and you plug it into either of the original equations. Which equation do you want? First one. Okay. So I'll plug x equals 3 into the first one. 3 plus y equals 6. Minus 3 from both sides. Y equals 3. And the very final answer is an ordered pair. X first, y second. So I'm going to sort of, in the steps box, fill out specifically what we did. Because the thing about these problems is you might sometimes start differently than somebody else does, especially when we get to the next set of examples. And so specifically what we did in step 2, when we found the variable that has opposite coefficients and we eliminated it, we eliminated y, is what we did in step 2. And in step 3, when we solved, we got x equals 3. In step 4, when it says plug that answer back in, specifically, this is what we did. We plugged x equals 3 into the first equation. We didn't have to, but that's what we did. So in case you were looking at your work later and you're like, wait, what did we do? But that's specifically what we did, even though those steps are general. Right? You try problem number 2. Just as a quick setup, which variable x or y has the opposite coefficients? X, right? Because the top one is a negative 1 and the bottom is a positive 1. So start there. All right, so the x's have the opposite signs. So we add those two equations. That drops out. What's y plus y? 2y. And then 2 plus 14, 16. Divide by 2, y. Y equals 8. What am I going to do with that? Plug it in where? Where would I plug it in? Either one. Which one would you like? Which equation? Okay. That's x plus 8 equals 14. Minus 8x equals 6. Your final answer is 6, 8. Who did that problem? I got that one? Okay. So that was our basic example. It was pretty much the heavy lifting of the problem was already done, making sure that there were some coefficients that were opposite. And so what we did specifically was in number 2, step 2, we eliminated x. We solved for y and got 8. We plugged that in to the second equation. And then we got our answer. Here we wrote it as an ordered pair. What we're going to do now is be given some problems where nothing is automatically opposites of each other. We're going to have to do the math to get them there. And what I'm going to do to set you up for that first is just some other sort of questions I have for you. Okay, so these were our basic examples, and these are our less basic examples. But first, a selfie. No, just kidding. The first question, so this is just sort of a lead-in to those problems down here. The first thing I want to know is, what would you say is the opposite of 5? Negative 5? Okay. What do you get when you add 5 and its opposite? What do you get? 0. Okay. Are 2 and negative 3 opposites? No, right? But we can use multiplication to make 2 and negative 3 into new numbers that are opposites of each other. So let's think about that for a second. So we're going to start with 2 and negative 3. And our goal is to multiply them by something. It doesn't have to be the same thing. And that will give us other numbers that are opposites of each other. Okay, that means the number is the same and the signs are opposite. Yes, sir. Okay, multiply by 2 by 3. And that would give me 6. And then multiply that one by 2, because then that would give me negative 6. So I'd multiply that negative 3 by a 2. Okay. Now 3 and 2 aren't my only options, but they're the really good options. Okay. So I took the 2 and the negative 3. I figured out some number that would be opposite, and then figure out what I had to multiply those by to get that number. So it got me to 6 and negative 6. Now what happens when we add 6 and negative 6? What happens? We get 0, right? They cancel each other out. Okay? They cancel each other out. And that's going to be the goal in this next problem. So if you look at this example, 4x minus 3y equals 9, 7x plus 2y equals negative 6. Look at your x coefficients, 4 and 7. They are not opposites of each other. Look at the y's, negative 3 and 2. They are not opposites of each other. So there's nothing that automatically eliminates right here. So we have to do some math to make that happen. Did you notice on the y it's negative 3 and 2, just like this example right here? All right, so if I'm looking at the y's, and here's one clue that I can start with the y. They already have opposite signs. So that's a good place to start. Okay? And so I want the same number to be in front of the y's, and we said to go from negative 3 to 6, I would multiply by 2. But I can't just multiply the y by 2, because it changes the value of the equation. I have to multiply everything in that equation by 2 to keep it in balance. And then if I want the bottom, this 2y, to be 6, I multiply everything by 3. Okay? So we said negative 3 times 2, that's what we did up there, and then 2 times a 3. And if looking at all of that at one time is too much information for your brain, you can always just sort of tell yourself, okay, I'm going to start here with negative 3 and 2, write it out here somewhere, and then do that work like we did over there. Okay? In case all this other stuff just sort of gets in the way of your brain. And you would say, okay, that's 2. Multiply that by 3. And then you would do that next. So now what we've got is distributive property on the top, distributive property on the bottom. And here's what our new equations would look like. 8x minus 6y equals 18. 21x plus 6y equals negative 18. So now when you look at the y values, the coefficients are opposite of each other. And so what will happen to the y's when I add those two equations? When you add opposites, what happens? They cancel out, right? So the y's will be gone. It's just an accident that the numbers on the right-hand side are also opposites. That's just a coincidence, okay? That's not going to happen every time. Yes. So here we go. We're going to add. I have 8 x's. I'm adding 21. That is 29x. When I add negative 6y and positive 6y, they are gone. They're eliminated, right? That's why it's called elimination method. Go back to your seat, please, sir. Just during the lesson. And then on the right-hand side, 18 and negative 18 is 0. Again, that's just a coincidence. Okay. So then we divide both sides by 29. And we get x equals 0. One thing I want to point out before we go further, the steps right here in the box, the steps are all exactly the same as the previous page, just with this one additional thing. Multiply one or both equations to make one of the variables have opposite coefficients. That's what we did with the y's. That's the step where we multiplied by 2 on the top and 3 on the bottom. And then real quickly, now that I know that x is 0, how do I find y? Plug it in. Now here's the thing, you have like 4 options now. You have the 2 original equations, and then you have these 2 new equations. It really doesn't matter which one you use. They're all equivalent, or we'll give you the correct answer. I recommend you use one of the original ones because the numbers are smaller. So which equation would you like? Top? Okay. So 4 times x, which is now 0, minus 3y equals 9. That goes away because that's 0. Negative 3y equals 9. Divide by negative 3. Y equals negative 3. So my final answer is 0, negative 3. Try the next example. It's at the top of your second page. Which of the variables already has, you know that song, right? Yeah. I know, I can't help it. You're lucky I don't say it more often. I rein it in about half the time. I do try and control it. It's not always successful. I'm trying to get on. I already started the recording. So let's. Oh, yesterday? Hold on. All right. So looking at this example, which variable has opposite signs already? Like that'll be the where you start, right? It's a clue, and it's the y's. And so this one's already negative 3. I really, really want this one to have what in front of it? I would really like for this y to be positive 3. Okay? So I have to do what? Times it by positive 3. But I have to do everything. Okay, and that distributes through. And then I actually don't have to change the second one at all, right? In the first example, we had to change both. But see, we don't have to do that every time, just in this one. So when I distribute that 3 through, I get 9x plus 3y equals 15. And then I bring down the other equation. I add them. So 9x plus 2x is 11. These are gone. 15 plus 7 is 22. Divide. Good. That's 2, right? X equals 2. So then I take that 2 and I plug it back into one of the equations. Which one do you want? First or second? First? Oh, too slow. So first I'm going to take x equals 2 up there. 3 times 2 plus y equals 5. Math, math, math. Go, go, go. Solve, solve, solve. Y equals negative 1. Okay. So we got that down. Okay, we did simple ones, then we did ones where we had to make the coefficients opposite. So now we're going to put all this together in a word problem, and then we'll be done for the day. This word problem is exercise again. Yesterday we had exercise word problem. This one's more realistic than the people running 1 mile an hour yesterday or whatever they were doing yesterday. That was not even running. So we have a word problem, and apparently when I'm typing stuff up, I think I'm being funny, and then I forget I have that there until I'm up here teaching, and I'm like, oh, that's it's not really funny up here. It's funny when I'm typing it. Wow. So here we go. Mark went to the gym. He did 40 minutes of Bikram hot yoga. You know what that is? It's yoga, but they turn the temperature up really, really hot so that you like sweat more. Or I guess you're sweating out your toxins or your calories, sweating out your McDonald's. Hayden, Focus. So he did 40 minutes of that and 10 minutes of jumping jacks, and he burned 510 calories. Yeah. That would actually be really hard.
That's actually a good exercise.
Jumping jacks? Yeah, it really is. The next time he went to the gym, he did 30 minutes of Bikram hot yoga and 20 minutes of jumping jacks, burning 470 calories. How many calories were burned for each minute of yoga, and how many calories were burned for each minute of jumping jacks? By the way, jumping jacks is a whole body exercise. It's pretty good. It's a pretty good. So for a word problem, I always recommend you start by figuring out what it is you're looking for. Don't even think about the rest of the problem. Don't even worry about the fact that there's 1,000 words and your brain wants to shut down because you hate word problems. Just zero in on what you're trying to find, and then we'll think about everything else, okay? So let's talk about it. Let's talk about what we're looking for, right? We're looking for two different things. The first one is how many calories were burned for each minute of yoga. So we're looking for number of calories burned for yoga. Give me a variable for that. What do you want? X, okay. And then the next thing is how many calories were burned for jumping jacks. So number of calories burned for the jacks. What variable you want? Y? Okay. So then we need to put all the information into equation form. So here's what we got. Here's our first bit of information. Okay. 40 minutes of yoga and 10 minutes of jumping jacks means 510 calories. Here's our second bit of information that we're going to use for the second equation. So with the teal colored highlighted stuff, 40 minutes of hot yoga, number of calories burned per minute is X. How do I combine that 40 and that X? What do I do with them? The 40 and X, how do they relate to each other? It's 40 minutes of yoga, X calories per minute. What, am I going to add those, multiply those? Or let me put it this way. Let's say I knew how much he burned. If he went 40 minutes of yoga and burned 5 calories per minute, what would you do with those numbers to figure out how many calories he burned altogether? Multiply. So if it's 40 minutes of yoga and he burned 5 calories per minute, you would do 40 times 5 and say he burned 200 calories, right? But we don't know that it's 5 calories per minute. We know that it's X. So it's going to be 40X. Okay? 40 minutes, and X represents the calories for each minute. Yeah. And then for jumping jacks, that's Y, and he did 10 minutes of it. So how many calories did he burn altogether? 10 times Y. And then for the whole sweat sesh, I hate shortcuts like that when people say stuff like that. You know, do you know what I'm talking about? Like on wherever or whatever. I hate those shortcut words. Sweat sesh. All together, he burned 510 calories. And what am I going to do with these two things? Plus, right? So what do you think for the yellow information? What's my equation going to look like? I thought we threw that away. Didn't we throw that away? Did you have another water? No. So for the yellow information, 30 minutes of yoga, 20 minutes of jumping jacks, 470 altogether. What's that equation going to be? 30x plus 20y. Good, equals 470. All right, so now here's what's up. First of all, these are in standard form, right? The x and y's are on the left. The constant is on the right. This would be a terrible problem for substitution or graphing. Graphing, if we try to put that in y equals mx plus b form, that would be a headache. Well, we could do x and y intercepts, but still. Substitution would be awful. We'd have to solve for the x or y and plug it back in. But elimination is going to make this much more manageable. We just have to figure out which variable we want to eliminate. But here's my question for you. The two examples we just did, one of the variables, they didn't have the same numbers in front, but they already had opposite signs. What do you notice about the x and y here? They're all positive. That none of them have opposite signs yet. So we're going to have to do even a little bit more thinking to figure out how to get these to cancel out. So it doesn't matter which one you do. You can start with the x or the y. I have a preferred one. Look at them and try to think like a teacher. Which one would cause less work to get their coefficients to be the same number? Do you think x or y? Yeah, the y would, right? Because 10 times 2 would give me the 20, right? And then I wouldn't have to change that 20 at all. So I only have to mess around with that first equation. If I was starting with the x and I was trying to do 40 and 30, I'd have to multiply the 40 by something and the 30 by something to get a new number. But with the y's, I only have to do 10 times 2 to get 20. The problem is, if I do 10 times 2 to get 20, okay, that would look like this. That's a good start. But they wouldn't have opposite signs, so they wouldn't cancel out. So negative 2. That's exactly right. You see that? So the 2 gives me 20. The negative 2 gives me the opposite sign. So now I'm going to distribute that negative 2 through, and I'm going to write it right underneath this bottom equation because I'm about to add them. So I get negative 2 times 40 is negative 80x. 10 times negative 2 is negative 20y. And then 510 times negative 2 is negative 1020. And I'm going to add these two equations right here. Okay? So 30 minus 80 is negative 50x. The y's cancel. And then 470 minus 1020 is negative 550. What do I do there to solve? Divide. Divide by what? Yeah. And so x equals positive 11. Now sometimes in a problem like this, you see how there's all those negatives right there? I'll get students who will just stop and they'll freak out and they're like, but Miss F, it's a real world problem. It's not supposed to have negative numbers. That's okay. You see how it figured itself out by the end? Okay? It's only at the end that you don't want a negative number. You want to be sure it's in context. But it's okay in the process of the problem. So x equals 11, but I still need to know y. So I take that x, I plug it into a different equation. Which equation do you want? Top or bottom? Bottom? Okay. So 30 times x, which is now 11, plus 20y equals 470. So 30 times 11, what's 3 times 11? 33, and then we add that 0 on the end. What do I do next? Yes, ma'am. Subtract 330. So that gives me 20y equals 140. Now what? Yep. Divide by 20. Y equals 7. Now, why am I not going to write this as parenthesis 11, comma 7 parenthesis? It's a real world problem, and a word problem gets a word answer. So some kind of real quick sentence, you could say, Mark burned 11 calories per minute. That was for yoga, right? By the way, I do not like yoga. Why not? Because, well, for one thing, it's hard, and then you're just sitting in there holding the position thinking about how hard it is. I know. I don't have mental toughness. I don't think it's peaceful. I like just sitting there shaking and sweating. I'd rather do like 30 seconds of something really, really hard, and then 30 seconds of something else really, really hard, or go running or something. Does it? I have never experienced that benefit of it. I must be doing it. I must be approaching it wrong. Even yesterday, my work doing, what was the other one? Jacks.